Organizers for inviting me to talk here. I'm really happy to be able to tell you about some of my own research that I do here with various graduate students and undergraduates and also collaborators in other places. And so this is the topic of my talk. So I spend my time, I'm gonna turn this down a little bit. There we go. Yeah, I spend my time working on a lot of fun things. What I think is the most fun part of physics, which are the very theoretical areas, trying to understand the physics of the whole universe and unified theories. And so I'm going to talk about some of these things today and explain what some of these pictures are. And so my general area of research that I mainly focus on is quantum gravity. So I'll tell you about that. And in order to start telling you about that, I'm just going to tell you a little bit about, just remind you a little bit about the regular theory of gravity that is basically accepted by everyone at this point, okay? And so that was Einstein's improvement on Newton's theory of gravity. And Einstein completely changed how we understand the physics of gravity. So you've probably heard of general relativity. This is basically the idea that to explain orbits, things following other kinds of gravitational interactions, we have this idea that space itself, the place where everything lives, is not just some background where stuff moves around it. It has its own dynamics. And so Einstein said that the way to understand gravity is when you have energy or mass or momentum in the space, it actually warps the space that everything lives in, or more precisely, it warps the space-time that everything lives in. And then when you're in this warped space, if you have other things moving around in there, if they just travel on their natural paths through this warped space-time, then you see interesting things like orbits and things falling towards the Earth. Okay. So that's a kind of completely different picture from Newton, who was thinking of a fixed background space-time and then forces on top of that. So because I'm going to mention it later in the talk, I actually decided to write the very simple looking equations that we use to study Einstein's theory of general relativity. And so it's really basically a simple concept. The left-hand side is a quantity that tells you at any point in space-time, how is that space curved? And we can picture that a lot better if it's like a two-dimensional space. So is it flat? Is it curved like a sphere? Is it curved like a saddle where it curves one way in one direction and another way in another direction? And so all of that information is contained in this thing, which is basically just a matrix, a 4x4 matrix of numbers. So that has all the information about how space is curved at a single point. And then on the right-hand side, you have a constant. That's just the Newton gravitational constant. And then this thing is another 4x4 matrix of numbers that tells you how much energy density you have at that same point in space, how much momentum density, and how much energy flow, and how much momentum flow. Okay, so that is called the stress energy tensor. And then Einstein's equation says that those are simply proportional to one another. And so that means if you have some energy and momentum or flow of those things, then you're going to have some curvature in your space at that point. And so with these equations, we can then predict how space-time geometry will evolve with time if we know what stuff is in the space. So in my example here, I imagine that I have two bodies that are about to orbit each other, and then I can take that as my initial conditions for Einstein's equations. I can solve the equations, and then that will tell you that not only do these things orbit around each other, but they warp space in a particular way, and they produce these gravitational waves that are carried away from the orbiting pair of bodies. So that's one really interesting prediction of Einstein's equations that we've recently directly verified because we can now observe these gravitational waves with LIGO. Another really fascinating prediction of Einstein's equations that we also now have observational evidence for is the existence of black holes. And so if again you use those same equations and start by imagining that there's just a bunch of matter distributed, and there's enough of that in a small enough region, and then you solve the equations, they will predict that this thing will collapse basically without end and warp space-time so much that there's a region where nothing can escape. That where inside here, there are none of these natural paths, either for massive objects or even for light, where you could get from the inside to the outside. Okay, so the boundary of this thing is what we call a black hole horizon, and this is an example of a black hole. Another really amazing prediction of general relativity of Einstein's equations is that it is impossible to have a universe which is filled with stuff, where you have some overall energy density and where the universe just sits there. According to Einstein's equations, if you want a universe that has some overall energy density, then that universe either has to be expanding or it has to be contracting. And for quite a while now, we have observations that tell us that in our universe, which we think of is basically filled with stuff, the expanding case is what we're observing. Okay. And so that's really interesting. If you take that observation, you use Einstein's equations, and then you basically do the opposite thing, extrapolate backward based on what we observe today, then the equations predict that sometime in the past 13, 14 billion years ago, there was a time when the density, which today is decreasing, extrapolating back, you get increasing, and 14 billion years ago, according to the equations, it just goes to infinity. So everything was infinitely dense, and we kind of call that the Big Bang. So in the last two slides, I've written these question marks. These are things where, according to Einstein's equation, something just goes to infinity. The density of stuff goes to infinity in the middle of a black hole if you solve the equations. The density of stuff goes to infinity at the beginning of the universe if you solve the equations. And we would say that that's kind of a thing that makes Einstein's theory of gravity incomplete. We just don't really understand what that infinity means. And so people think that if you really want to understand the question marks, you need to improve on Einstein's theory of gravity, and specifically, you need to bring in the rules of quantum mechanics. Okay, so this is one of the motivations why people want to come up with a quantum version of general relativity or quantum version of Einstein's equations. That motivation being that there's just stuff in the regular theory that we don't think we can possibly understand. So a really kind of naive explanation for why it is that we think quantum would be important for that. Okay. Because normally we think of quantum mechanics as being something that you need to understand atoms and molecules and tiny microscopic things. But when we think of gravity or black holes, we're imagining really huge things. And so the reason why we could say, well, maybe quantum should be important here or here, one reason we could give is just imagine that we make things denser and denser and denser and denser and denser. Okay. Well, at some point, stuff is going to be so dense that even at atomic distance scales, gravitational forces will start to become important. So if you imagine the hydrogen atom, where of course you need quantum mechanics to understand that, and now you imagine the proton has the mass of the sun, and the electron has the mass of the Earth, because we've just made everything so dense, then of course gravity will be important there. So that is one kind of motivation for quantum gravity, for why you would want to understand that. Another motivation is kind of more abstract. We live in this universe. We think that the universe definitely is described by quantum rules fundamentally, at least to describe some physics. We need quantum mechanics. We also know that there's gravity in our universe. And as a theoretical physicist, I would say there should be some kind of complete mathematical description that's underlying the physics that we observe. Okay, so there should be, there should be some kind of consistent set of rules that explains all the stuff that we see. And those set of rules have to include gravity, have to include quantum mechanics. And so there should be something that ties those together. And so that would be the theory of quantum gravity that we'll look for. In a little bit, I'm going to tell you actually that there's a much better reason why you should care about quantum gravity, but let's postpone that for now. So people were pretty successful when they came up with quantum mechanics in the early 20th century. They were able to come up with a quantum version of the mechanics of ordinary objects that help us understand things like hydrogen atoms and other kinds of atoms and molecules, doing the quantum mechanics of charged particles interacting with each other. And then they went on to something harder, which was understanding the quantum mechanics of electromagnetic fields, which are also a very important part of our classical physics. And that turned out to take maybe a couple of decades to really do that. But in the end, it was basically not so much different than doing quantum mechanics for particles. And so you just apply a certain set of rules, and you start with the classical theory of electromagnetism, it's written down by Maxwell, incorporate the quantum rules, and then you get something called quantum electromagnetism, or QED, and that works really well. So we've understood how to do that, and that's actually the best tested theory in all of science. We can make predictions with quantum electrodynamics, do measurements in laboratories, and match these things to like 8 decimal places. We've extended quantum electrodynamics to what's called the standard model of particle physics that I'm sure you've heard of. And that basically is just adding in some extra kinds of particles, some extra kinds of interactions, but it's still very much like the quantum version of electrodynamics. Okay, and that works really well. But it turns out if you want to try to then incorporate gravity, it seems to be a lot harder. And what we think now, after like half a century of doing trying to do quantum gravity research, is that it's just not as simple as saying quantum gravity is the quantum version of general relativity. So we think you can't just take Einstein's theory and then apply the rules of quantum mechanics like we did for electromagnetism. And as a kind of analogy for why that might be a bad idea, for why we've been failing in doing that, you can imagine a similar set of equations to Einstein's equations. There's a set of equations that we use to describe hydrodynamics. We want to describe water and the fluid dynamics of water. Then there's a set of fluid dynamics equations, and those have a lot of similarities with the equations of general relativity. Both of these things, have waves, and both of these things are difficult to solve. So you might say, okay, well, how do I do the quantum mechanics of water? And so the wrong approach would be to take the hydrodynamics equations and try to apply the rules of quantum mechanics to those. Because to do the quantum mechanics of water correctly, you really need to understand that water is not just fundamentally some continuous wave. It's actually made of some different, more fundamental degrees of freedom, which are the water molecules. And so to really do the quantum mechanics of water, you have to realize that the actual basic degrees of freedom of water are little particles, and then you apply the quantum mechanics to those particles, and then you get the right quantum theory of water. Okay. So it seems now that something similar is going on for gravity. Okay? Space-time is not made of water molecules, but it may be emerging from some more fundamental degrees of freedom, and we started to find evidence for that. Now, what are these fundamental degrees of freedom of space-time? Turns out they're much more bizarre than you would ever imagine. And so what we think right now in our best models of quantum gravity is that the fundamental degrees of freedom of space-time are not even things that live in our three-dimensional space. What we think is that there are some fundamental degrees of freedom that are actually some lower dimensional system, and our 3D physics kind of emerges from that somehow. Okay, so the stuff that we experience in 3D is not quite as real as we think. And the next bunch of slides, I'm going to try to tell you what the heck that means, what I just said. So we call this approach, this kind of best understanding that we have right now of quantum gravity, we call this the holographic approach to quantum gravity. And so we use the word holographic because that's a good analogy. When you have a hologram, that's like a piece of photographic film that is storing somehow the information about a 3D scheme. And if you do the right thing, you can recover the 3D image from the 2D photographic film. And so that's basically, in a way, how these quantum gravity models work. Another analogy that I like to give before I tell you the details is you can imagine playing a 3D video game on your computer. Okay, so the video game might have a whole 3D world, it might have rules of physics, you throw stuff, whatever. But then there's underlying that picture something more fundamental, which would be a computer chip inside of your computer that has little bits that are turning off and switching between zeros and ones. And there's some rules of physics that tell you how the computer chip operates. Okay, and then that is encoding, that's the more fundamental thing that's encoding what's going on in your screen. Okay, so there's a computer chip, which is more real. Then there's a code that tells you how to go from all the ones and zeros to Minecraft or whatever, where you're moving around and living in the 3D world, the virtual 3D world. Okay, so that is roughly how holographic quantum gravity says the real world might work. Okay, so it says that the 3D universe, that's what I'm drawing on this side, those are supposed to be like galaxies living in space. So the 3D universe with dynamical space is maybe more fundamentally described by some hidden two-dimensional system that we're not really aware of. And so that's what I'm trying to draw here. Okay, so let's try to give you a good mental picture of what this two-dimensional system might be like. Okay, so I want you to just imagine an ordinary ball of stuff. Okay, think of a thin shell of copper or lead, or if we want to be fancy, it could be graphene, and that would be really thin. And so that's kind of what I mean by a two-dimensional system. There's not really any thickness to this. But it is a more or less ordinary physical system. And this thing is something where just obeys the rules of quantum mechanics. We can write down in Hamiltonian, we can use the Schrodinger equation to predict the evolution. And you can add energy, it can have waves. It's pretty much an ordinary kind of physical system that we're used to dealing with. Okay. So this physical system, like a ball of graphene, it could have various different quantum states. It can have states with less energy or more energy, or combinations, superpositions of states with different energies. And so the idea here is that for every one of these states of the 2D system, somehow that would be encoding the physics of a 3D universe. Okay, so depending on the details, which particular state you pick, you would have a different geometry, maybe different amount of matter inside your space, and that could be arranged in a different way. So I'm going to give you some examples of that. So in quantum mechanical systems, often the very simplest kind of state that we can think of would be a state where you cool the system all the way down to absolute zero. We normally can't do that in practice, but we can think about it theoretically. We always like to ask about what is the ground state of a system in quantum mechanics. And so if you took this particular 2D system, cooled it all the way down to absolute zero, and then asked what physics and gravity does that encode, well, you might be not surprised to learn that that is the way to encode completely empty space. So the vacuum state of your theory corresponds to a totally empty universe. The next thing you might imagine doing is adding a little bit of energy to your object. Okay, so here I've just come along with a hammer in the laboratory where this 2D system lives. I give it a little tap. And so that's added some energy, which then spreads around the two-dimensional system. And then we could ask, what does that do on the gravity side? When I add a little bit of energy to that system like this. And according to the map, what that does is it encodes a space-time which is now not totally empty, but instead it has some gravitational waves moving through the space. So that's almost the simplest thing you could have apart from empty space. It's just empty space with a few ripples on it. If I wanted to instead, I could add a lot of energy to my two-dimensional ball of stuff. Okay, so I could maybe put it in an oven, heat it up until the temperature is really high. And then I could ask, well, what sort of thing does that encode in the gravity side of the picture? And so it turns out that that is how you would describe, from the holographic perspective, from the 2D language, a giant black hole in the middle of an otherwise empty space. Okay, so both of these things are spherically symmetric. We're thinking about an equilibrium high temperature state where the energy is uniformly distributed on the sphere. And on the gravity side, you're also adding a lot of energy. And the kind of most symmetric way to do that is just to have a big spherical black hole. Okay, and so there's this kind of remarkable connection between kind of thermal physics in this side of the story and black hole physics on this side of the story. And so that actually connects with something that people like Stephen Hawking and Jacob Bekenstein were stumbling upon in the 1970s. Back then, they were using Einstein's equations to understand the classical physics of black holes. And they noticed there were various things that were true about black holes that reminded them a lot about things that were true in thermodynamics. So for example, they could prove using Einstein's equations that the area of this event horizon, the place where you cannot return from, the area of that thing always increases no matter what you do. And that sounded like the second law of thermodynamics, where entropy always increases no matter what you try to do. They also showed something that sounded just like the first law of thermodynamics that relates the changes in energy to the temperature and the change in entropy. Right? So they showed that there was an equation relating the change in the area of that horizon with the change in the mass of the black hole and the amount of gravity at the location of the horizon. Okay? So that was called the first law of black hole mechanics. So there was almost this perfect analogy between stuff that's true about black holes and stuff that's true about thermodynamic systems. And now with this holographic quantum gravity approach, we can understand why that would be true, because we're saying if you have a black hole, there's actually this underlying picture. The more fundamental degrees of freedom are just in a very hot state at a certain temperature. So this is an ordinary thermodynamic system. The rules of thermodynamics definitely apply there. And so those, if you understand the right way to map over the quantities, where it turns out entropy here corresponds to the area of the horizon here, and energy here corresponds to mass there, then you can see why it would be that black holes satisfy laws that look like thermodynamics laws. Okay. So I've basically just told you all of these things, and it might not at all be obvious, well, how would we know that? If we have quantum states of this 2D system, how would we kind of figure out that those things I just said are the space-times that those quantum states are encoding? So this was a major question. What is the encoding map? If someone gives me a quantum state for this 2D system, how would I figure out what the geometry of space-time is and what's in the space-time? So I'm about to tell you the answer to that question. And the interesting thing that we've discovered in the last 10 or 15 years is that a really important part of that answer has to do with quantum entanglement, which again, I'm sure you've heard a bit about, but I will go over the basics of that. Okay, so this is going to be a crucial element of this decoding map that will allow us to go from the quantum state to the space-time picture. So for the purposes of this talk, we need to know very little about quantum entanglement. So I'll just kind of remind you what it is in a really basic example. So a nice example of a quantum system that has entanglement would be a hydrogen atom. And so, you know, hydrogen atom is an electron, proton, and we can think about the ground state of the hydrogen atom where the electron is in this 1s orbital, spherically symmetric, surrounding the proton. If you want a more complete description of the lowest energy state of hydrogen, you also have to take into account the fact that the proton and the electron have a spin. Okay, and so we just visualize that as a little arrow pointing in some direction. And you could ask, okay, what are the spins doing in the lowest energy state of hydrogen? And so it turns out that in that state, neither the electron nor the proton have a definite spin direction. Okay, the state of the spins in the ground state of hydrogen is this kind of very quantum state. And so what this means is a state where you have the proton spin pointing in one direction and the electron spin pointing in the opposite direction, okay? But then there's a quantum superposition of that state with another state where things are flipped. And so this is the way we would write the quantum state of the spins in the ground state of hydrogen. And so in this state, neither the proton spin or the electron has a definite orientation. Like I said, if you were to go and measure like the z component of the proton spin in this state, there'd be a 50% chance you'd find it pointing up and a 50% chance you'd find it pointing down. Same thing with the electron spin. So neither of those individual spins have a definite direction. But those two spins are perfectly correlated in this quantum state, in the sense that if you were to measure the electron spin and find it to be up, you will definitely find the proton spin to be down. Okay, and if you measure the electron spin to be down, you will definitely find the proton spin to be up. And so that's a kind of correlation that's possible when you have states that are these quantum superpositions, and that correlation is what we call entanglement. Okay, so entanglement is when you have a two-part system, neither part has a definite state, but there's a correlation between the two parts in the way that I've described. So for the next couple of slides, I want to have a nice visual way to represent when we have a two-part quantum system and there's entanglement between the two parts. And so instead of writing all of that out every time, I'm going to make a shorthand of that and represent it using this picture. Okay, so this picture represents a proton and an electron, and the little squiggly green line is my representation of quantum entanglement. So that's telling me that some aspect of these two systems is correlated in this quantum way. It's going to be useful to actually quantify that entanglement in more complicated systems. And just for this system with the two spins, we could say, you know, if they don't have that correlation, we could just say it's zero entanglement. And if they have that specific correlation, we could call that 1 unit of entanglement. The technical term is entanglement entropy. So when I say that, it's just a way to quantify how much of this entanglement you have. Okay. So let me think about a slightly more complicated example where it'll make more sense what I mean by quantifying the entanglement. And so in this system right here, I have a whole bunch of different particles. Maybe they're all protons, or maybe they're all electrons, or maybe there's some electrons and some protons. And you see that each different particle here happens to be entangled with one other particle in the ring. Okay, so it's a particular pattern of entanglement. And I can then look at some subsystems of the full system. Okay, so subsystem A is the system containing those three particles. And what we notice about subsystem A is that each one of those particles is entangled with something else outside the system, outside the subsystem. And so for this subsystem, we would say we have 3 of these entanglement units because each particle has 1 unit. It's entangled with something outside A. Okay, that has 3 units of entanglement. Subsystem B, on the other hand, has particles that are entangled, but they're entangled with particles within the subsystem. So there's not actually any entanglement between this subsystem B and the rest of the system. And so we would say there are 0 units of entanglement for subsystem B. Okay, and I could give you an exercise to figure out what is the amount of entanglement in this subsystem. And so hopefully you can see that that one would have 2 units. And whatever system I choose, you could just figure out how much entanglement that has. Okay. So remarkably, you now know enough for me to explain completely the decoding map that allows you to go from a quantum state of one of these holographic systems to the geometry of space-time that it would be encoded. So let me do that in the next slide. Okay. So instead of drawing the two-dimensional ball, I'm going to simplify it a little bit. Okay, so I'm imagining a lower dimensional version of this holographic quantum gravity, where I would have a one-dimensional thing like a ring, and then that's going to be encoding the geometry of a two-dimensional space. Okay, and so here's my one-dimensional ring. I'm visualizing it as being made of a bunch of particles, and you'll notice these particles have various entanglements with other particles. Okay, so these green ones are just indicating a pattern of entanglement between the different particles. On the right-hand side, I've drawn an example of a two-dimensional space. So this would be like a space-time or just the spatial geometry. For some universe, that's 2D instead of 3D. Okay, and so I want to tell you how do I take the quantum state of this system, an arbitrary quantum state, and then figure out what geometry that it's encoding. Okay. And so let's say I start with quantum state. And so just like in the last example, I can consider various subsystems. So here is a subsystem between A and B. Okay, so that's a bunch of these particles. And I can ask how much entanglement does that subsystem have? Right? And so that'll be a number. And I can look at a different subsystem and ask how much entanglement does that other subsystem have, and that'll be a different number. Okay, so you'll notice there's like a lot of information there that would tell me how all the different parts, how much entanglement they have with the rest of the system. Setting that aside for now, let's think about this geometry. And now I think about a geometry question, which is starting with any 2 points on the boundary. What is the shortest distance path between those 2 points in the geometry? And so if this were just a flat disk, there'd be one answer to that. But if it's curvy, there'd be a different answer. And so again, I can ask that question about any 2 points on the boundary of this disk. Okay, so that's a bunch of numbers, that's a bunch of numbers. And so this map is just saying, if I have a quantum state and I calculate all these entanglements, how much is each part entangled? The geometry that it's encoding is the geometry where the lengths that I just described match with the entanglement entropies over here. Okay, and so if I've got this shape right, and I look at the entanglement of this region, then that's going to be equal to the length in this geometry. And then if I look at the entanglement of some other region over here, that will be equal to the length from that one endpoint to the other endpoint over here. So that might go through here. Okay, so it turns out that this is a mathematical question that can be solved if you have a ring and I say, I want to find a geometry where the distance between this point and this point is this. If you specify all these distances, you can find the geometry, and basically that's how the code works. So that is a simple map between entanglements of a lower dimensional quantum system and the geometry of a higher dimensional quantum system. And that was proposed by these guys, Ryu and Takanagi, to be the way that holographic quantum gravity works. That the entanglement pattern of 2D system. So now we just have to imagine going from the ring to the ball. And so we can still ask about different parts of the ball, like a disc on the top of the ball, and how much is that entangled with the rest. And then instead of just these paths, the higher dimensional generalization of that is if I have a disc on the top, and then there would be some surface through the geometry. So we're going to be talking about the least area surface rather than the least distance path. Okay, so you just take this, move it up one dimension, and these guys said that's how it works. That's how holographic quantum gravity is able to encode the geometry of the space-time in the entanglement pattern of the quantum state. These guys, for that observation, they just won the Dirac Medal in 2024, and that's basically the highest honor that's specifically for theoretical physicists. And so that was just very recently. Okay. So that was like a very cool thing. I mean, both kind of at a mathematical level. You could map from entanglement structure to ordinary geometry, and the fact that it's just so simple. But it actually has some kind of shocking implications. And so this is one of the things that I thought about in my research like a while, more than a decade now. So let me tell you a kind of shocking implication of that, what I just told you. So let's say we have this state of our lower dimensional quantum system, and it has this pattern of entanglement, and it's describing this space-time geometry according to the map that I just described. But now, because this is an ordinary system, we can consider different states. You can imagine this in our lab somewhere, and we could like do measurements, and we can do things that would reduce the amount of entanglement. Okay, so a good way to do that in the hydrogen atom, you just measure the spin of the proton, and then that actually destroys all the entanglement between the electron and the proton. After that, we just have a definite state. Okay, so you can imagine doing the same thing with our holographic quantum gravity system. You do something like measurement that would destroy the entanglement between this side and this side. What does that mean about the space-time geometry? So if there's no more entanglement between this side and this side, then the entanglement of that subsystem is just zero. And that means that the distance through space between this point up here and this point has to go to zero. Okay, so it means that if you disentangle the two sides of your 2D system, then the 3D system kind of pinches off, and now it's split into two parts. And then you can keep removing entanglement. You just keep cutting, measure half of this so that you kill the entanglement. If you just keep doing that until there's basically no entanglement left, then that means all the distances are just zero. There is no space-time left once you've removed all the entanglement. Okay, and so that's kind of shocking because space-time is something that we thought was just like a nice classical concept that we didn't need to think about quantum mechanics at all to understand space-time. But actually what this is saying is that space-time fundamentally is an intrinsically quantum phenomenon, that there are these underlying degrees of freedom, this underlying 2D system, and in order to get the space-time at all on this side, you need to have entanglement, which is only possible with quantum mechanics. All right, so another very cool thing that happens in this story, once you believe that the geometry of space has something to do with entanglement, we can go back and ask whether the dynamics of space, so the physics of Einstein's equations, whether that has some more fundamental underlying explanation related to the physics of entanglement. And so it turns out that there are a lot of things that people have learned about entanglement. Mostly people that were caring about quantum computation, where entanglement is really important, or another field called quantum information theory. So people just ask questions about how different parts of a quantum system could be entangled with each other, and they derived things like this. These are constraints that have to be obeyed by entanglements. This is a quantum system with 3 different parts. There's a pattern of entanglement. And basically it says that no matter how we try to connect everything up, if you look at the amount of entanglement of A with the rest of the system, that's SA, and you look at the amount of entanglement of B with the rest of the system, and C with the rest of the system, then you have to obey these inequalities. You can actually prove this later if you want. Based on what I've told you so far, you can show that those have to be true. Okay, so these are constraints that every set of entanglements has to obey these constraints. And if we're talking about a holographic gravity system, then those things should translate to something that would be true about geometries, that every geometry has to satisfy a certain constraint, and only certain geometries are allowed. And so a while ago, with a graduate student, Mike McDermott, and a postdoc, Neva Lashari, who's now a professor at Purdue, we were wondering, well, could we find the specific set, some specific things that would be true about entanglements that would imply the equations for gravity? Okay, and so it turned out we were able to do that at least in situations where the curvatures aren't too big. So if you start with empty space, which we said was corresponding to the vacuum state of our 2D quantum system, and then you think of an arbitrary perturbation of that, an arbitrary way to add a little bit of energy to that system. Okay, so now we've got a state which is the vacuum plus a small change. And so it turned out people had derived this rule for how the entanglement is allowed to change in that case. And it is this. And what it says is that if you look at any ball-shaped region A, anywhere on the sphere, any size, then when I do this perturbation, the change in the entanglement of this region is always necessarily related to how much energy that I add in the region. Okay, so that's what delta E of x, that's like the way that the energy that I've added is distributed throughout that region. And f of x is just some function. So I kind of integrate this function against that function, and that tells me how the entanglement changes. I can't separately change the entanglement and the energy density in any way I want. Always has to obey this equation. Okay? And so this is something that translates over here to a statement about what kind of perturbations to empty space are allowed. If I now think of like all the possible consistent ways that I could go from empty space and now add a bit of stuff to it, then it turns out that this implies that adding the stuff to this space can only be done in a way that satisfies Einstein's equations. Okay, and so you get a derivation of the Einstein's equations, at least for small curvatures, but so we do this perturbatively to linear order and then also to second order. So you're really uncovering the nonlinear physics of general relativity from something that just has to do with entanglement in lower dimensions. Okay. So this is when I was saying there's actually a much better reason to want to understand quantum gravity other than these really exotic things like the Big Bang and black holes. Well, the reason is that it seems like even classical gravity has this underlying quantum mechanical description. And so it gives you a deeper understanding of what's going on, just like Einstein's equations gave us a deeper understanding, a more correct understanding of Newton's theory. Okay, so in the last 15 minutes of the talk, I want to ask the question, does this kind of beautiful picture of the origin of space-time and gravity, does that actually tell us anything about the real world? Okay. And so there are a couple of like apparent barriers to making use of this new description of gravity and applying it to the universe that we live in. And so one of the problems is, I'll start with this one. When we're thinking about these holographic quantum gravity systems, we're thinking of different states and what kind of space-times that they correspond to. Okay, so basically all the finite energy states of the 2D system, they map over to space-times which could have lots of interesting stuff. You could have a black hole or multiple black holes or a bunch of black holes and some gravitational waves. But all that stuff is localized in some region. And then far away, the space is basically empty and static. Whereas in the universe that we happen to live in, we think that the stuff in the universe kind of goes on for as far as the universe goes on. We assume in cosmology that the universe is basically uniformly filled with stuff. And so you don't get to an empty region if you just go far enough in one direction. Okay. And of course, we also think our universe is not just static. I told you that it has to be expanding if it's filled with stuff or contracting. Okay, so this is an apparent tension. Another apparent tension that is preventing us from making this contact is that if we look at the details of the expansion of our universe, since 1999, we've known that the expansion is actually accelerating. It's getting faster. And the simplest way to explain that is to say that our universe has a positive cosmological constant. And that basically that means that there's this kind of energy density, what we call dark energy, that fills space and has a positive value. And that's the simplest way to explain this acceleration. The first holographic quantum gravity models actually came out about the same time, not 1999, but 1997. And it turned out those models give you theories of gravity, which also have a cosmological constant, an energy that fills space and doesn't change with time. But unfortunately, the energy density predicted in these models is negative, while the energy density that seems to explain our observations is positive. And so for most of the last 25 years, people have just been thinking that, well, that doesn't really have to do with exactly with our own universe, and we have to generalize this somehow to describe physics that we observe. Okay. So I want to focus on that issue and explore it a little bit more. So just to be a little bit more precise about what we're talking about here, let me tell you about exactly how we model the evolution of the universe. And so you can start with Einstein's equations. You can put in the assumption that the universe is more or less uniformly filled with stuff. And then you end up with this equation. And it's an equation for what's called the scale factor. So A is a measure of, let's say, how far apart stuff is in the universe. So you could maybe take it to be the distance between two very widely separated galaxies. And as the universe expands, that distance expands. And the left-hand side of this equation is just how does that scale factor change with time? It's the derivative of A over A squared. And what the Einstein equation tells you is that that thing on the left is equal to a constant times the energy density on the right-hand side. Okay, so this is why we say you can't have this be zero, you can't have a static universe if this is not zero. Okay. So our standard model of cosmology, which is called the lambda CDM model, just expands on that, and it says the energy is due to ordinary matter, where the density here gets smaller as A gets bigger. Okay, so the universe doubles in size. You don't get more dust all of a sudden, and so the energy density of dust drops by this doubling factor of the volume. The radiation also gets diluted, but by even more because there's a dilution, but also the wavelengths get stretched out by the expansion of the universe. So it goes to a lower energy kind of electromagnetic radiation. And then in the standard model, we have this term, which is the positive dark energy. Okay, so this is just a number. It is constant throughout space and time. So that is, when you hear people talking about the lambda CDM model, that's all it is. Okay, and as I said, when you have that being positive, you get this acceleration. And actually, it just accelerates forever. So it just keeps expanding forever, getting faster and faster. If you take the holographic quantum gravity models, as I was saying, they typically have the opposite sign for the dark energy. Okay. And so in the simplest cosmological solutions of those models, what happens is your universe starts expanding. And actually, I should have said it in the last slide, but basically these become less and less important as the universe expands. The matter dilutes, the radiation dilutes. This doesn't dilute, and so at some point it takes over. And if it's negative, instead of making the universe accelerate, it makes the universe decelerate and then crunch. It falls right back on itself, and we get what's called a big crunch. Okay, and so this kind of thing is just unrealistic because we can observe that our universe had a period of acceleration. And so you might want to rule out these holographic models for the real world. But what I, with my collaborators, have kind of realized in the last few years is that this is actually not the generic behavior of cosmological solutions of holographic gravity theories. Okay, so there's an interesting thing that's often overlooked about these theories, which is that in addition to space-time expanding, they also have another element in them. So we have expanding space-time. They typically have other stuff like matter and electromagnetic fields that live in the space-time. But there's one other element that these theories almost always have, which is a thing called a scalar field. And so what is that? Well, you know what an electric field is and a magnetic field. It's just a thing that exists everywhere in space, and it has a certain magnitude and a certain direction. A scalar field is a thing that exists everywhere in space that has a value, but it doesn't have any direction. So it's just a number everywhere. And these holographic gravity models say that there are typically some of those scalar fields sitting around. And furthermore, that they typically will change with time in a cosmological solution. Okay. So in order to understand the effect of those, we basically need to know how much energy density they have, because that's what's coming into the right-hand side of our Friedmann equation to figure out the evolution of the universe. Okay, and so how do you know how much energy density one of these scalar fields has? Well, there's going to be a picture like this, which shows you how much energy you have depending on what value does your scalar field take. This is a slightly more complicated situation where we have a couple of these scalar fields that can each take a different value, and then this would show you what is the energy density for this field being 1 and this field being 0. So we get that energy density. All right, so the important thing to take away from this picture is the following. So if you set these scalar fields to 0, then we're living, that corresponds to this point here, which is kind of like a little local maximum of the potential, and it has a negative value. So when we say these holographic quantum gravity models have a negative cosmological constant, what we mean is if you set the fields to 0, then the energy density in that case is negative. Okay. And so the cosmological solutions that I was just showing you, they have the universe expanding and contracting, and that whole time, the scalar fields just sit there at 0. Okay. So the equations that govern the evolution of these scalar fields are actually pretty much the same equations that would govern the motion of a particle in this sort of potential. Okay. So you can just imagine a ball rolling around, and you say, okay, what are all the possible solutions to that equation that governs the ball rolling around in that landscape? And so, yes, there is one solution where the ball is carefully perched right in the middle there, where the potential is flat, and so it can stay there. But you definitely wouldn't say that's the generic solution of that physical system. Okay, and so in the same way, if I think about cosmology models coming with these theories where you have the scalar fields, you can have solutions where those scalar fields are just sitting at 0. But again, definitely wouldn't say that's the generic thing that would happen. A much more generic thing to happen would be, this starts somewhere else on a slope, and then it rolls down, and maybe it rolls up again. And so then we could ask, well, what kind of cosmology would that give? And if we didn't just place the scalar field perched on that location there. And so what we conclude is that, okay, well, maybe generically it starts over here where the potential energy is positive. Maybe that's what's happening in the Big Bang. And the universe expands and the scalar field rolls down. And then maybe when the matter and radiation dilute enough, the scalar fields are still over here where the potential is positive. And then we would get acceleration because we haven't gone down into this negative region yet. Okay, so we have the positive energy, the universe would accelerate. Eventually, maybe the scalar fields would roll down to the negative values of potential, and then we'd start to decelerate, and eventually we would crunch. And so this is, I would say, kind of a more generic prediction. If you have a holographic quantum gravity model and you want to say what happens in cosmology, then I would say this situation where you have the bang, there might be a bit of acceleration, then it decelerates and eventually it crunches. That's your prediction. And so that could definitely be consistent with what we're observing for our universe. So maybe like we just happen to be here in the universe, we've seen the Big Bang, the accelerating part, but we haven't yet got to the decelerating part. That'll happen sometime in the future. And so then it's really interesting to ask, is this compatible with our observations? So could that actually be what happens in the real universe? Okay. And so fortunately, there's just a massive obvious prediction of this model versus the standard model of cosmology. And that is in these models, if we're accelerating, then we're sitting on the slope. And so if we go forward in time, the scalar field's going to go down and we'll have less dark energy in the future. But if we look back in time, we would predict more dark energy in the past, not a constant dark energy. And that has observational implications. And so as a simple model to explore that, what we could do is basically say, hey, maybe we don't understand the whole potential here, but if we're sitting there right now and we want to know what happened in the recent past, we can do a Taylor approximation of the potential and just model it by a straight line, okay? Or, add quadratic terms if we want to. And so my student, Chris Waddell, and I decided that we were going to just take this model, which has a parameter that tells you how much energy density you have now, but then also a parameter that has how much the energy density is changing, or the slope of this potential, okay? And given values for those parameters, and given the current value of how much matter density we have in the universe, and given the current value of how quickly the universe is expanding, so these four numbers given as inputs give you an output, which is a theoretical value for this scale factor evolution. And if V1 is not 0, that'll be a different sort of evolution than in the lambda CDM model, where the V1 is 0. And so we can distinguish them. And so what we can do is then try to compare with data. Okay, so the data we have for the scale factor evolution, one big data set that tells us about how the universe is expanded is just by looking at all these supernovae that we've observed that have happened at various times in the past, and by comparing their redshift and their brightness in a way that if you ask me afterwards, I can explain. We can kind of piece together how the universe has been expanding. Another set of data is just looking at the large scale structure, how the galaxies are arranged, and you compare, well, how were the older, dimmer galaxies arranged back when the light from them started coming, and how are the more recent galaxies arranged? And you could sort of piece together this picture, this observational picture of how the universe has been expanding. Okay, so we compared the model with the data, and so that's what this plot is showing. So this is kind of a standard, they call it a likelihood analysis. These are two of the parameters. This is the dark energy value at the present day. This is the slope of that potential, which tells us how quickly the dark energy would be changing. And then these contours kind of show which models give the best fit to the observational data. Okay, so let's focus on the blue contours that describe both data sets, supernova and large-scale structure evolution. And so what we found is that, so this is like a 95% confidence interval. So according to a standard likelihood analysis, the usual model that we use for cosmology, the lambda CDM model, is sort of sitting way out there outside the 95% confidence interval. Okay. And so what the conclusion here is that it seems that this dark energy fits the data better if you assume that it's changing with time. Okay, and not only if you look at V1 equals 1 or 2, so this could have been 0.1 or 0.01, could have been that we found, okay, maybe it's better if it's changing with time, but only changing a tiny bit. But this is something where the dark energy would have changed by an order of 1 amount, like it's half as much as it was 5 billion years ago. And that's actually fitting the data better. Okay. So I'm basically out of time. This is my last slide. I had wormholes in the title, but I just want to throw this out. It could be something you ask me about later. A very cool feature, this is the right story. There's a very cool thing that happens at a mathematical level when you describe these universes that have a big bang and a big crunch. They kind of have a more like a time symmetry where you have the universe being small, like dense here and dense here. And it turns out that mathematically in this kind of universe, it's natural. There's an interpretation for imaginary values of time. And so in this mathematical way that we treat these systems, we can ask, well, what does the universe look like in the imaginary time direction? And so it turns out that there's this natural, what we call a wormhole geometry, living at imaginary values of time, where going to minus infinity and plus infinity in imaginary time, we have kind of an empty space region that kind of looks like the empty space that we needed in order to give a holographic description. And so the way that we're ending up using holography to describe the real universe is to say that instead of like a real 2D system, there's some, I don't know, imaginary 2D system. There's a 2D system that lives at that is out here in imaginary time somewhere. I should probably stop there. Let me thank you all for coming, and also I'd like to thank all of these sponsors for the conference. Yeah, totally, yeah.
All right. Well, thank you, Mark, for that excellent talk. That was awesome. And for everyone else, thank you for making our second day and our first full day of CupC go as smoothly as you made it go. It effectively is over for today, but we still do have a room set aside in Henny's 200, which is where we've kind of been meeting generally. That we will have that room until 10, so you are all welcome to gather there, hang out. There will be board games and whatnot. And I believe Mark said that he might also come over as well.
Yeah, so I'd love to hear your questions, and so I'll be available to chat afterwards.
Yeah, so with that, thank you all, and go wherever you please.
Sure. Yeah.
Like reading the line, but I get to ask a question first.
Yeah.
I was wondering how you